Welcome, folks, to the seventh lectures and the second one in the overvoltage uh, transient or overvoltage transient voltages, you can say, uh, in power system. Overvoltages are there, a steady state, power frequency also, but the concern more is about the transient overvoltages which last very short. We learned in the last lecture uh, two things: the basic insulation level and the switching insulation level. The basic insulation concept came first when the rated voltages of the transmission lines or transmission network was below 400 kV. At that time, the the transient overvoltage which played important role was the lightning impulse, that is the uh, external source of transient overvoltage, because the switching over voltages magnitude depend upon the rated voltage, that is 2 to 3 or even 3.3 per unit is the level of switching over voltages. The magnitude of switching over voltages below 400 kV rated voltages was not a concern, was not uh, a damaging factor. So the basic insulation level was designed with the concept of the transient maximum magnitude of transient overvoltage produced by lightning impulse, and it was restricted to a certain level. That means the highest uh, transient overvoltage produced by lightning strikes on the network was known, and that was taken care, and accordingly the basic insulation concept to be provided to the network uh, was developed. But when the transmission voltages increased to beyond 400 kV level, the magnitude of switching impulse voltage, that is uh, the SIL, is increased with respect to the rated voltage, because it is proportional to the rated voltages of the system. As you know, we have learned the 800 kV rated voltage system is very common all over the world. 1000 kV, 1150 kV are also in practice, may not be to a wide scale, but up to 800 kV transmission, AC transmission voltages are very common. So every transmission line and also the substation connected to the transmission lines need overvoltage protection. The overvoltage protection in power system is a very common feature, and that must be always practiced. All overhead transmission lines above 33 kV. 33 kV, you can say, is a distribution line. Very often 33 kV lines are underground also, which are not vulnerable to, for example, lightning strikes. So 33 kV lines are provided with all overhead transmission lines above 33 kV are provided with a ground wire. You might have observed in every high voltage transmission line, on the top there is a thinner conductor. Sometimes there are two conductors which are actually the ground conductors on the topmost position, and they run along with the line continuously all over the line. Even an open air substation is provided on the top, a network of thin wires or uh, tall lightning uh, lightning conductors installed on tall masts, and that is all for the protection from lightning strikes. That means the topmost wire, as I mentioned, is a grounded wire, and when the lightning strikes, the discharge current is given path towards the ground, and it doesn't do any damage in that case. Sometimes there are two overhead topmost position ground conductors when the width of the transmission line is very large. So there is a way, uh, I mean, an envelope, you can say, uh, a conductor on the top protects all other installations below there. I mean, the topmost conductor is ground, which conducts the discharge current to the ground, and it provides an envelope, a volume below there, under which the installations are protected from the lightning strike. Then over voltages are produced by circuit breaker operations in the network, also travel over the conductors and spread in every direction. And the overvoltage produced on the phase wires or on the live wires need to be protected. Uh, I mean, the insulation provided everywhere. Insulation is provided. Let be the let be the phase conductor, or which is connected further in the substation with the gadgets, transformers, circuit breakers, CTs, PTs, everything. Everything is provided a level of insulation, either basic insulation or the switching impulse level of insulation, uh, switching impulse level, SIL, what we call it to be. So the over voltages produced in the form of traveling waves damage or can damage the insulation. So the insulation level provided must be adequate to withstand the over voltage. And when the over voltages are of very high magnitude, we provide a over voltage protection called surge diverter. It is a better and common known name. Earlier, it was very commonly known as lightning arrestor, because the the significance of overvoltage was only from lightning strikes. The significance of overvoltage produced by switching operation was not there. When the when the level of transmission lines voltage was lower, as I mentioned, every insulator string on the transmission line is also provided with a horn gap, or the rod gap, we call it sometimes horn gap or rod gap, to protect from overvoltage. The insulated string, uh, the insulated string from dangerous overvoltages, but also attenuates. It does not protect only from overvoltage, but also attenuates the peak intensity of the overvoltage traveling wave. We also learned how do the lightning arrestor or the surge diverters function in the last lecture in detail, that they uh, let the peak of the overvoltage uh, grounded and not less let pass towards the uh, direction traveling wave is traveling. The peak, that means the voltage across the lightning arrestor is able to propagate further, and it is cut by the peak value of it. So the voltage which develops across the lightning arrestor is known, and that is called residual voltage of the lightning arrestor. That is a rated voltage for every surge diverter or lightning arrestor. So that only that magnitude of overvoltage is let travel further. The peak is grounded. Yeah, uh, just a minute. Yeah, I was mentioning the horn gap or the rod gap in the insulator string. This figure, as you see, is a insulator string. The top conductor is the high voltage conductor, and the bottom one is the grounded electrode conductor. And in between, the uh, at both the position, at the high voltage as well as at the ground position, metallic conductor is given, and as you can see, the gap, air gap of the between the two metallic conductors is very small. So you can imagine air has got even otherwise much smaller dielectric strength as compared to the solid dielectric of the insulator. In this case, this is a porcelain insulator. The dielectric strength is much higher. Still, we would like, if the transient overvoltage comes in the form of a traveling waves, here it comes here. The there is the across the two electrodes, this one and this one, a flashover occurs above the specified magnitude, because the gap distance will determine at which the flashover can occur there. When the flashover occurs here, the traveling wave is the peak of the traveling wave is grounded, but since it is traveling, uh, it is it is able to proceed further as a traveling wave, but there is an attenuation in its maximum magnitude. So that means the traveling wave attenuates while traveling over the conductor at every insulator installed at the poles, and that is how this works like a protection. This is specifically a protection. This horn gap or the rod gap works like a protection for the insulator, and in the process it also attenuates the magnitude, the highest magnitude of the traveling wave. A small statistics is given here. Lightning in Japan causes more than 50% failures of high voltage transmission lines. This is a statistics available from Japan. The we have learned the surge diverter or the lightning arrestors, malfunctioning of the surge diverters, a crucial device, could be one of the reasons also. Along with the horn gap, the more sophisticated, more proven gadget used for protection of transmission line or transmission network is the surge diverters. And the surge diverters often malfunction. And when they malfunction, they let they do not ground the peak magnitude of the traveling wave and let the total magnitude of traveling wave reach the substation or to the gadgets installed on the transmission lines at substations. And when higher voltage reaches there, it may cause insulation failure. So this is a very big problem, uh, malfunctioning of the surge diverter. Why were they malfunctioning? The Just a minute. The type of uh, yeah, the type of surge diverters we have learned about the surge diverters used in the past were of not good quality or good. They were designed with the older concept. They used to have uh, air gap in between. Air gap electrodes used to get corroded, and there used to be expulsion type of lightning arresters which would uh, produce a flashover between the air gap and let the uh, traveling wave grounded, the peak of the traveling wave grounded. And those old type of lightning arresters used to, I mean, when the electrode, you can imagine, howsoever well sealed unit it may be, over the time the electrodes get corroded. The flashover voltage between any two electrode may get may be different over the time. So they used to malfunction when higher flashover voltage because of the corrosion is there. When they should do the flashover for the over voltage, they are not doing. That means they are letting the higher magnitude of the over voltage pass on to the network. So the life, you can say, of the lightning arresters because of their construction was very short as compared to the transmission lines. So they needed frequent maintenance or frequent replacements. And when it was not being done, when people were trying, but it happens that there was malfunctioning of the lightning arresters. The concept of lightning arrestor with the development in technology changed. The solid lightning arrestor with the material of zinc oxide ZnO was developed. Pellets of blocks of zinc oxide were brought together to the required number, and there was no air gap, you can say, no open or in the closed chamber, no air gap between two electrodes in these newer type of uh, lightning arresters, and they function more reliably than the earlier type of lightning arresters. So zinc oxide lightning arresters, as we have also learned, so to say, any lightning arrestor provides a very uh, uh, provides a short circuit path to a very short duration pulse voltage. People have called that short duration pulse voltage also high frequency voltage. There is no frequency involved in it. It is single pulse. How can there be a frequency involved with it? So you can say they have a characteristic, zinc oxide has a characteristic to provide low impedance path to the short duration pulse, but a very high impedance path for the power frequency voltages or current. So the power frequency voltage or current is not able to pass through, but the high frequency transient over voltage in the form of traveling wave would get grounded at these arrestors, zinc oxide. So this is a characteristic of zinc oxide arrestors or zinc oxide material, so to say. Now we have learned that there are ground wires, there are horn gaps, there are lightning arrestors installed in the network. What is the role of all these? Is to protect from both the types of overvoltages, transient overvoltages, that is produced by lightning as well as produced by switching impulse. Now, when the question of designing the level of insulation to individual gadgets, one of the most important gadget for the design has been, and it is still today there, which involves a lot of insulation, is the power transformer. So what should be the level of basic level of insulation? That is what we have also learned, basic insulation level of the transformers. Later, the concept of switching impulse level of the transformer had to be designed. So if you designed for the highest transient over voltage, you may have to provide very high level of insulation. That means high level of higher cost for the equipment, for the transformers. So if you had good system to not let very high transient over voltage reach the transformer at all, you may get along with lower level of BIL or SIL, whatever is necessary depending upon the rated voltage of the gadget. So that is how a system of insulation developed. And that system of insulation is called the insulation coordination in high voltage power network. The term insulation coordination is defined, mind it, very important. You can read it, I'll read it out for you and explain, as the correlation of electrical equipment insulation level with respect to the characteristic of protective devices if provided. Mind it, I said not every uh, not every level of distribution network may be provided with protective devices. Nowadays, it is being provided, even that 33 kV. The concepts have changed such that the equipment is protected from excessive overvoltage. So this coordination, which has to take into consideration the highest voltage which the equipment concerned may get when the traveling wave of transient overvoltage is coming by passing the uh, protective device, and that protective device is the arrestor, surge arrestor. And what voltage can reach or pass beyond the surge arrestor is nothing but the residual voltage of the surge arrestor. So the level of the gadgets, level of insulation of the gadgets has to be designed with respect to the characteristic of the surge arrestors. Lightning and switching over voltages occurring together is possible, but the probability is very low. So they are not considered the situation when lightning and switching may take place together. there may be always some gap, time gap for these two types of overvoltages taking place in the network. Providing the basic insulation level, that is BIL, to the system so that it could withstand the severest of lightning overvoltage. As we have learned also that the basic insulation level is decided by the severest of the lightning overvoltage produced in the network, and uh, it was established over the time with experience and calculations that transmission voltages beyond 400 kV, the requirement of the system insulation level itself became so high. That means for say 800 kV transmission system, the basic insulation of the system became so high that it could perform in a better way against the known highest magnitude of lightning over voltage. So you can say the significance of lightning over voltage in the network at 800 kV and above was diminished. What determined the insulation level there was the overvoltages produced because of switching surges, which are proportional to the rated voltage itself, which are uh, as written here. The system voltages of 800 kV and above, the switching over voltages become the main criterion for insulation design, which may have a range of variation from 2 to 3.3 per unit. The switching over voltages may vary from 2 to 3.3 per unit. Yeah, so the basic insulation level BIL for lightning impulse is defined as the electrical withstand voltage of insulation expressed in terms of the crest value of the standard lightning impulse by the IEC, the International Electrotechnical Commission 71. And BIL is chosen correctly relative to the prevailing protective level, that is protecting devices, under which the horn gap and the lightning arrestors come. The equipment will have an adequate insulation level to withstand the prevailing switching surges also. If this is taken care, the switching level in these system is at 400 kV and below. So the switching over voltages are not very high, so they are taken care of with the lightning impulse voltage. That means the protection for lightning impulse voltage. Yeah, I can imagine one question must be coming in your mind. When the whole network is provided with a grounded wire on the top, which is supposed to uh, let the lightning discharge current go towards the ground and protect the system below. Why are we providing so much? Why are we so much concerned with the lightning over voltages? Still, we are concerned with the lightning over voltages. Why? The reason is that in spite of providing the grounded conductor on the top of the network, there are occasions when the lightning strikes on the live conductors below the grounded wire. It does happen. So you can say the grounded wire on the top of the system or the top of the network do not provide foolproof condition that the lightning will not reach the live conductors. Yeah, how the process of adoption of the mm, uh, practices adopted for insulation coordination, that is uh, 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 yeah. As you can see here, a system designer must have clear knowledge about this aspect while dimensioning the system insulation for 400 kV and above transmission network. That means the system designer must have good knowledge of the prevalent over voltages in the network, the protective devices, the function of the protective devices, and the insulation level provided to the network. Below 400 kV, I've been mentioning again and again, all the three techniques of protection, that is earth wires, rod gaps, as well as lightning arresters, are provided on the transmission lines and substations. Newly developed metal oxide, as I mentioned, the zinc oxide surge diverters, or commonly known as lightning arresters, are installed at the substations, which cater to the need of both switching as well as lightning over voltage transients or the traveling waves. They are installed at the substations. They are not installed on every pole of the transmission line, but they are installed at the substations. At the in the transmission line, the insulation is the insulator string, or the insulator string, we call it. Earlier it was, even today, very commonly of porcelain, then glass, fiberglass, uh, um, toughened glass insulator strings, and now the fiberglass reinforced plastic insulators are installed, and they are provided, if required, they are provided with the horn gap, etc., to protect them there, then and there. But what is what can get more damaged and of our concern is the uh, um, main power transformer connected to the transmission lines at the substation, and also other gadgets at the substation. The level of insulation or the insulation provided to all these gadgets are of more concern for us, and that is why the lightning arresters or the surge diverters are installed at the end of the transmission line reaching the substation, or just outside or just beginning of the substation. That is the location where these are provided. So this is one of the practice, and we know the magnitude which the surge diverter will let pass to the to the substation, that is to the power transformer, and the power transformer should be provided with adequate insulation level to be able to withstand the residual voltage formed by the lightning arrestor. Yeah, that is what I have described. The role of such diverters in insulation coordination. You can you can read it once again, and here, uh, yeah, yeah, I've discussed practically everything in this slide, what is written there. Anyway, you should read it and I'll read it out. Surge diverters, also called surge arresters, play an extremely important role in the implementation of insulation coordination. Uh, the surge diverters protect the equipment in transmission and distribution network from the incoming lightning and switching surge in the form of traveling waves. Yeah, the let me mention here the overvoltages developed at quite most often uh, mm, in the transmission network at high voltage by lightning strike on because the transmission lines extend over thousands of kilometers, so they are exposed to the atmosphere. Switching operation takes place at every substation at high voltage, and over voltages are produced. So the over voltages are produced on the mainly on the transmission network, but once produced, they spread in every direction depending upon the impedance of the path. And ultimately, that high voltage surge, where does it end up? It ends up at the consumer level of the power. That is why you might have seen sometimes the intensity of light at home suddenly increases for a very short duration, and then it comes back to the normal level. And that is how the energy is consumed in the network. And see the transmit the over voltage transient waves are also carrying some energy, and that energy has to be consumed somewhere. And that is how, as I explained, that is consumed at the consumer level. When the over voltage reaches the consumer voltage, higher energy is consumed. Let it be a gadget, uh, suppose it's a heater, for a small duration, microseconds or milliseconds, the heater will give more of heat, there will be more of light from the lighting gadget, and that is how the energy is consumed at the consumer level. Yeah, we have also learned about uh, the the surge diverters provide low impedance path or an alternate low resistance path to ground for the transient impulse type voltages, that is the short duration uh, pulse, uh, and the so-called high frequency transient over voltages, what they what some people have called it to be. I would not like to call it to be high frequency because there is no frequency involved. It's only a pulse produced by lightning strikes and also by opening the circuit breakers. That is switching surge, how they are produced. We have learned in detail in the last lecture. We have also learned the role of surge diverters in our uh, in the network. We have uh, uh, already gone in detail. Now, yeah, the surge diverters, as I said, they have a characteristic that they do not let pass the power frequency voltage, and the volt time characteristic of the device must be below the withstand voltage of the protected apparatus. That means the protected apparatus, this is, for example, transformer, the level of voltage, level of insulation provided to the transformer should be able to withstand uh, the residual voltage, as we have been talking about. It should be capable of conducting high voltage, high frequency, again high frequency, or the high voltage short duration impulse surge currents and recover its dielectric strength quickly. That means it should uh, let when the short duration pulse comes, it provides conducting path, but it recovers the material, that is zinc oxide, the lightning arrestor or the surge diverter material used these days. Zinc oxide has a characteristic that it recovers after the pulse is passed. It's it recovers its impedance offered to the uh, voltage or the current, and it does not allow any power frequency voltage or current to pass through, and it should not allow power frequency follow-up current, that is also known as follow-up current. So because the power frequency voltage and current is always there, so it should continuously uh, 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 give high impedance path to the power frequency voltages and currents. Hmm? Yeah, this figure uh, we had discussed in the last lecture in detail. As you can see, this is the uh, characteristic of average. Uh, no, sorry, this is the characteristic of the lightning arrestor or the surge diverter residual voltage, and which is let pass to the mm, network beyond the arrestor. This one is able to pass, and the red one, as you can see, the original wave shape of the overvoltage and the peak of the overvoltage uh, is grounded, you can say, with the help of arrestor. Once again, it is being explained, and whereas the basic insulation level, or so to say, in the case of very high voltage network 800 kV, the SIL also should be above the residual voltage. Basic BIL, or also you can say SIL level, should be above the arrestor residual voltage, so that with the help of lightning arrestor or the surge diverters installation, we can reduce the basic or insulation level or the switching impulse level to a great extent, and economize in the cost of the production of such gadgets. So, with uh, this, this is a simple uh, substation, uh, as it is just a schematic drawn for the three-phase lines, how they are connected. They are connected over the insulators to the from the poles, or here also they are everywhere. The high voltage conductors are supported by the insulators, and insulators are provided with the rod gap or the horn gap, and as you can see it here, the insulators are provided with rod gap and horn gap, and this is the conductor is coming to a transformer, as you can see it here, is coming to a transformer, and within, I mean, in the transformer, the voltage is brought with the help of a bushing. This is a bushing, and bushing is also provided with these rod gap or the horn gaps, so that the bushing insulator is protected when a flash occurs in air, not over the not over the bushing insulation. The bushing insulation is protected with the help of these horn caps. And this is a very common and most simple, yeah, methods of insulation coordination we have uh, uh, discussed. Uh, There are conventional and deterministic method mostly applied to tower system voltages, and statistical approach. It is a probability based method used for higher system voltages, etc. They are when you go more deep in the subject of insulation coordination, if you would come across all these things. So yeah, conventional method. I think it is not so important. This is what I talked about, expulsion type of lightning arrestors, which had a mm, arc chamber within the, as you can see here, which had an arc chamber. That means a flashover is occurring within the arrestor. Nowadays, these such type of lightning arrestors or such diverters are no more in use. And as I mentioned, the zinc oxide arrestors, which do not have any arcing chamber, or which do not have the air gap in between the within the arrestor, so they are the zinc oxide arrestors perform in a better way and reliably over the time. Yeah, we discussed the lightning, the generation of over voltages and their protection and the insulation coordination in this chapter. It was necessary for you to learn at this stage because when we go to the equipment production, the insulation level is provided to every gadget considering the over voltages. And these, the lightning and switching impulse over voltages prevail in every network. And accordingly, in the laboratory techniques, every gadget has to be tested with lightning, and many of them, the requirement today is also for switching impulse voltages, because an insulation would withstand much higher lightning impulse voltage as compared to the switching impulse voltage. Because it's a slower wave, the breakdown strength is lower for with switching impulse voltage. Lightning impulse voltage can be would be withstood by every insulation of highest magnitude. We'll learn when we go to the laboratory techniques. Thank you very much for today, and then we'll see you in the fourth chapter next.